What's up, Algebros and Broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear! Hey, welcome. Today let's take a look at section 1.3. We're going to talk about vector equations. Vectors. A matrix with only one column is called a column vector, or simply referred to as a vector. And here we have just some examples as to how these could look. Here I have the vector u with the entries 5 and -8. 2 entries, just one column, 2 entries. V, vector v has entries 2/3, 1/4. Vector w, a little more sort of, mysterious, has entries w sub 1, w sub 2. And these are just vectors with 2 entries. We could have, vectors with more entries. I could have a vector for example, I could have a vector A with, 3 entries, 1, 3, 4. I could have a vector B with, let's say, 5 entries, -7, 2, -1, 3, 0. So all sorts of possibilities there. And, for what we're doing with vector notation, I'm usually just going to display that something is a vector. You can see that these things are written as vectors, but some common notations involve using an arrowhead notation, sometimes a hat notation to show that something is a vector. But, I'm not going to really be too strict about that notation here in the lectures. So if you're not sure if something's a vector, you can always ask me. But otherwise, if I'm displaying it as a vector or calling it a vector, then we know it's a vector. We would say the set of all vectors with 2 entries is denoted as R2, and that's all of our Cartesian plane, all of our 2 space. But here we're saying the set of all vectors with 2 entries, so every possibility would be R2. Now, 2 vectors in R2 are only equal if and only if their corresponding entries are equal. So when we say 2 vectors are equal, we mean they're equal. Let's talk a bit about some vector arithmetic. And if you've seen Calc 3, if you've gone through that material yet, this is likely going to be not as exciting as I would want it to be, but it's still very necessary that we define these things and talk about them. We can add 2 vectors together by adding their components entry-wise. So here I have vector u given with entries 3, -7, vector v given with entries -5, 2, and if I want to find this new vector u plus v, well, I would take these vectors and I would add them together, and I would want to add them component-wise. So here, if I'm adding them component-wise, 3 plus -15, so adding the top components, the first components, 3 plus -15 gives me -12. And then adding the second components, -7 plus 2 gives me -5. And if I had more of these to do, I would add. So of course, we're noticing that if I'm going to add 2 vectors together, they have to have the same amount of components. I wouldn't be able to add a vector with 2 entries to a vector with 3 entries because I wouldn't really be able to do that last part of it since I'd be missing something. Just something to keep in mind. We can multiply vectors by scalars by multiplying each entry of the vector by the scalar. So if you have a vector u with entries 6 and -4, given a scalar, just a real number, c equals 3. I want to find c times u. So okay, c times u, and I'll use my notation there to sort of show which of these is the vector. It would be 3 times the vector 6 minus 4. And we would multiply each entry by the scalar, so 3 times 6 for the first entry, 3 times -4 for the second entry. 3 times 6 is going to give me 18. 3 times -4 gives me -12. And this is my vector c times u. So not so bad. Now let's take a look at a couple more examples. I don't want to, do too much of this. I think you'll probably get the hang of it pretty soon. Here I'm given vectors u and v. U has entries 3, -4. V has entries -2, 1. And let's find u plus v. We'll find u minus v. We'll find 3u plus 4v. and we'll find 5u minus 2v. Or you can find, others. You sort of go crazy with this stuff. But let's go ahead and start. So u plus v, I'd want to take these vectors and add them. We're adding component-wise. We're adding respective entries. So I add the first two entries together. 3 plus negative 2 gives me positive 1. I'm adding the second entries together. Negative 4 plus 1 gives me negative 3. And this gives me a new vector, u plus v. If I want u minus v, well, I can take this first vector, 3 minus 4, and then I can subtract away the second vector v, which had entries negative 2, 1. And I could think of this as subtraction. So here I could say 3 minus negative 2, that gives me 3 plus 2, gives me 5. And negative 4 minus 1 gives me negative 5. We'll talk about another way that we can envision this in just a bit. 3u plus 4v, of course. So now we have these scalars that we're working with. So I want 3 times vector u, which had entries 3 minus 4. I want to add to this 4 times vector v. Vector v had entries negative 2, 1. And if I go ahead and multiply these scalars in, I want to do that first. Say, okay, I multiply to both entries, so all of the entries really. 3 times 3 gives me 9. 3 times negative 4 gives me negative 12. And I'm adding to this. Here I have another vector. 4 times negative 2 gives me negative 8, and 4 times 1 gives me 4. And now I can add these together. So I'm still finding 3u plus 4v, but we should be able to get it in this next step here. 9 plus negative 8 gives me 1. A negative 12 plus 4 is going to give me negative 8. Then we had one more that we wanted, 5u minus 2v. Now what we could do, so we did the subtraction earlier with u minus v. I think it's perfectly reasonable and fine to just treat it like subtraction. We're comfortable with subtraction. But if you'd like to, you can think of this like adding with negative coefficients. And that's really what subtracting is, right? So I'd say, well, this is really 5u plus a negative 2v. I can think of it that way. So I want 5 times vector u plus, and then negative 2 times vector v. And we said vector u had entries 3 minus 4. Vector v had entries negative 2, 1. And then I can bring the scalars in first, right? So I could say, okay, 5 times vector u, 5 times 3 gives me 15. 5 times negative 4 gives me negative 20. And then I'm adding to this, I can bring negative 2 in. So I get the subtraction sort of when I do this, I can bring that negative 2 in lieu of subtracting and then just add. So negative 2 times negative 2 gives me positive 4. Negative 2 times 1 gives me negative 2. And then I can add these together. So I'll say, okay, 15 plus 4 gives me 19. Negative 20 plus negative 2 gives me negative 22. And there we have all of these new vectors we wanted to find, just vector arithmetic. Let's talk about some of these algebraic properties that we have with vectors. So for all vectors u, v, and w in Rn, these are just vectors in a vector space Rn, and for all scalars c and d, so c and d are just real numbers, we have the following properties. First, u plus v is equal to v plus u, so we get a nice commutative property here. Second, we can group u plus v and then add those and then add vector w to that. Or if I want to, I can add v and w together first and then add vector u to that. So we have a nice associativity property. Then I have u plus 0, 0 being the 0 vector, is equal to 0 plus the vector u, which is equal to u. So we have an additive identity. Fourth, I could say vector u plus negative 1 times vector u, or just call it minus u. That's the same as minus u plus u, which gives me the 0 vector out. And just to sort of be clear, I'll make little notes. This is the 0 vector, 0 vector. So here I get an additive inverse, where in particular negative u is really negative 1 times vector u. Fifth, we have a left distributive law. So here I have the sum of vectors u plus v, and I have the scalar c in front, and I can distribute that in c times vector u plus c times vector v. A sixth property here, I have a right distributive law. So here I have the sum of these scalars, c plus d, and then I'm multiplying that to vector u so I can distribute in from the right. So we get c times u plus d times u. Seventh, we can talk about working with scalars. So here I have scalar c times, and then I have the expression, the number, the scalar d times vector u. But if I'd like to, then I could regroup this into c times d, so multiplying the scalars first and then multiplying into the vector u. And lastly, we have 1 times vector u is equal to vector u, so we have a multiplicative identity. Really cool properties. I think we take a lot of these for granted, but it's important to discuss that we still have these properties when we move over into vectors. We still have all these nice properties. Linear combinations. So given the vectors v sub 1, v sub 2, all the way to v sub p in a vector space Rn, and given the scalars, these are just real numbers, c sub 1, c sub 2, so on and so forth to c sub p, the vector y defined by, and here we have y is equal to c sub 1 times vector v sub 1, plus c sub 2 times vector v sub 2, plus c sub 3 times vector v sub 3, plus so on and so forth, plus c sub p times vector v sub p. We call this the linear combination of the vectors v1, v2, so on and so forth to v sub p, with the weights, the scalar weights, c sub 1, c sub 2, so on and so forth to c sub p. Just to make sure that it's clear, the v's are the vectors, and the c's are the coefficients, the scalar weights. We'll talk about vector equations, though linear combinations are going to be incredibly important for the course. So, get making flashcards and remembering this idea right away, because we're going to talk about it quite a bit. Vector equations. A vector equation, x1 times a sub 1 plus x sub 2 times a sub 2 plus so on and so forth plus x sub n times a sub n equals b, has the same solution set as the linear system whose augmented matrix is the following. So here we have a coefficient matrix with a sub 1, a sub 2, so on and so forth to a sub n. We're augmenting with b. And in particular, we would say that b can be generated by a linear combination of these vectors a sub 1, a sub 2, so on and so forth to a sub n, if and only if there exists a solution to the linear system corresponding to the matrix. So we're hoping for something that's consistent. Let's get some practice with these new ways that we can write things. I want to write a system of equations that is equivalent to the given vector equation. Now, once you see what we're doing with this, you could likely just go right to writing the system of equations. I don't think it's too terrible to do, but if I sort of go through it bit by bit, the first thing I want to do is I want to bring my variable x sub 1 into this first vector like a scalar weight. So I get 4 times x sub 1, 7 times x sub 1, negative 5 times x sub 1. And I want to add to this, now I have this next vector, I want to bring x sub 2 in, multiplying it to all entries like a scalar weight. So I get 12x sub 2, negative 6x sub 2, I get 1x sub 2. And then you guessed it, I want to bring x sub 3 in to this next vector, so 3 times x sub 3. 0 times x sub 3 is really just 0. So I could write it as 0x sub 3. It makes no difference, really. And then another 3 times x sub 3. And then equals, and then here I have this next vector, 1, 4, minus 7. Now what I want to do is I want to think about adding these. And we already talked about vector addition. I just want to add corresponding components. So I could write this left-hand side all as one vector. I could say 4x sub 1 plus 12x sub 2 plus 3x sub 3 is the first entry. The second entry would be 7x sub 1 minus 6x sub 2 plus 0. 0x sub 3 if you want to write it that way. And the last entry would be negative 5x sub 1 plus x sub 2 plus 3x sub 3. And then this is equal to this vector 1, 4, minus 7. Now from this, we can start to really see our system of equations. Right? And the idea is that two vectors are only equal, and here I'm saying they are, if their corresponding entries are equal. So now what I can do is I can just sort of abandon the vector notation that I have here and just treat this as a system of equations. So I'll use a curly brace for the system. But the first equation should be this 4x1 plus 12x2 plus 3x3 equals 1. Second equation should be 7x sub 1 minus 6x sub 2 equals 4. And the third equation should be negative 5x sub 1 plus x sub 2 plus 3x sub 3 equals negative 7. And here notice I didn't bother with that 0x sub 3. I think it just, takes up space where it's not needed. But I don't want to fail to notice that x sub 3 is missing. But here's my three equations, three unknowns. Looks great. Looks really good. I'd like to write a vector equation that is equivalent to the given system of equations. So now I'm just sort of going backwards. And what I can do is I can try to think of this as scalar weights acting as, my variables acting as scalar weights rather, and then working with the coefficients from there. And I'm really just working backwards from what I just did. But I think that certainly if we can see what's happening, I can try to sort of, use my eyesight here to line up practically column-wise to see what's going on here. If I look at all these x sub 1 terms and think about the vector that it would multiply to, it would multiply by the coefficients on x sub 1. So it was 3x sub 1, negative 2 times x sub 1, and then 5 times x sub 1. So I can set that part up first. And then I can do the same for the others. So now I can move on to x sub 2 and think about how this vector would look for the coefficients on x sub 2. So it was negative 2 x sub 2, negative 7 x sub 2, and 4 x sub 2. And it looks like I got one more to go on x sub 3. And so let's go ahead and think about what the coefficients are. It's 4x sub 3, and then I had a 5x sub 3, and then a negative 3x sub 3, and then this is equal to, I have this vector on the other side, and this should just be what it's equal to, 3, 1, 2. And this is my vector equation. Let's take a look at an example. I want to determine if this vector b is a linear combination of these vectors a1, a2, and a3. Now, if that's going to be the case, we can think back to what our definition said just a bit ago. If b is a linear combination, then that means a1 times x sub 1 plus a2 times x sub 2 plus a3 times x sub 3 would be equal to b. For some scalar weights x1, x2, and x3, I'd be wanting to solve for those. And essentially what I can do is I can think of this as an augmented matrix system. So I can take a sub 1, a sub 2, and a sub 3 all as columns to building a matrix, and then I can augment this with vector b. And then I want to solve. I want to know, is there a solution? So that's really what we want to be doing. So it's familiar computation for us, just a new way to sort of think about it, a new way to word it. Here, this first column on a sub 1, I can just write that as a column vector, but I'm going to write it as a column to a matrix, a coefficient matrix, 1, 0, 1. My next column, negative 2, 3, negative 2. My next column should be negative 6, 7, 5. And then I'm going to augment this with the column vector 11, negative 5, 9. And I want to go through, I want to know, can I solve this? Is there some solution? Let's see if we can. Let's go through and do our best. So I'm going to start with some row reduction. I can use this 1 in the upper left corner to get zeros underneath it. So I'm really doing an operation then in row 3, replacing row 3 with row 3 minus row 1. What's the worst that could happen there? So let's say rewrite rows 1 and 2 just to start. Row 3, I get 1 minus 1 gives me 0. Negative 2 minus negative 2 gives me 0 as well. 5 minus negative 6, that's 5 plus 6, gives me 11. And then 9 minus 11 gives me negative 2. So far so good. If I want to reduce further, and you could really think about, scaling down row 3, so I do want to do that in a moment. But what I could do is I could work with scaling on rows 1 and 2. You can do this in some compound row replacement, which is perfectly fine, and I think, maybe the best way to do it. But it's still sort of the beginning of our semester together, so let me go ahead and do something a bit more. It's going to take a little bit more time, but I think it's going to be a little bit more manageable. We can see what's going on. I would scale up both of these rows. I would do 3 times row 1, and I would do 2 times row 2. And you'll see why in just a moment. So when I multiply everything in row 1 by a 3, I'm going to get 3, negative 6, negative 18, augmented with 33. I'll multiply everything in row 2 by a 2, so it gives me 0, 6, 14, negative 10, and I can just rewrite row 3. But the reason why I did this is so that I can try to eliminate this sort of middle entry of row 1. Right, so I did sort of get rid of my 1 as a leading entry momentarily, but I'm going to be able to scale it back. And I want to treat this 3 as a leading entry. I want to scale it eventually. I'm trying to get rid of this negative 2. And now that I've scaled it up to a negative 6, I scaled the 3 to a 6, I can eliminate it. So here I can actually work in row 1, and I can replace row 1 with row 1 plus row 2. So we'll say 3 plus 0 gives me 3. Negative 6 plus 6 gives me that 0 that I wanted. Negative 18 plus 14 gives me negative 4. And then augmented with 33 plus negative 10 is going to give me 23. And then I can rewrite row 2, so that was 0, 6, 14, augmented with minus 10, and I can rewrite row 3, 0, 0, 11, augmented with minus 2. Now to answer the question, we can probably answer it already, but let me just sort of really illustrate the point here. Let me scale these back down. So let me do a 1/3 row 1, trying to get the leading ones back. I would do a 1/6 row 2. So I'm trying to get these all as leading ones, and I would have to do a 1/11 row 3. So scaling these now, for row 1, I'm going to get 1, 0, negative 4/3, augmented with 23/3. For row 2, I'm going to get 0, 1. Here I'm going to get 14 divided by 6, and I can reduce that by 2. So that's going to give me 7/3. And then negative 10 divided by 6, I can reduce that also by 2, which should give me negative 5/3. And then scaling row 3, dividing everything by 11, I should get 0, 0, 1, augmented with negative 2/11. Now hopefully we can see from this that there is some solution that exists. We can go a bit further if it's not clear that the answer is quite yes. We say, well, we would still be able to reduce this. Is it going to look pretty? No, but we can find these values. So here I could replace row 1 with row 1 plus 4/3 row 3. And how would that look? Well, I would get 1 plus 4/3 times 0 is 1. 0 plus 4/3 times 0 is 0. Negative 4/3 plus 4/3 times 1 gives me another 0, that 0 that I wanted. And then this value here in the augmented section isn't really something I'm looking forward to computing, but I can just state that it's going to be 23/3 plus whatever 4/3 times minus 2/11 is. And I could go through the arithmetic, I get a common denominator, but the idea is that this is some, feasible thing. This is some number, it's going to give me a solution, right? Same idea here. I can replace row 2 with row 2 minus 7/3 row 3. That's going to give me 0, 1, and that's going to give me the 0 that I want, 7/3 minus 7/3 times 1. And then the augmented entry, it's not going to be, anything wonderful to look at, but it's a negative 5/3 minus 7/3 times negative 2/11, which we could switch this over to addition if we cared to. And then I can see what that third part of my solution is a bit better. That's 0, 0, 1 augmented with negative 2/11. So these numbers are there, so there is some solution. So to answer the question, remember what the question asked. Determine if B is a linear combination of A1, A2, and A3, and we can say yes. B is a linear combination of A1, A2, and A3. These are what the scalar weights would look like on the vectors A1, A2, and A3. They're not the nicest looking scalar weights, but they exist, and that's what they are. Let's take a look at another question. For what value or values of h is this vector y in the plane generated by v1 and v2? Now, this is really quite a similar question, so we're just kind of getting some exposure to how these questions can be phrased and what it really means that they're asking for. So for y to be in the plane generated by v1 and v2, And we'll talk about this notion of a plane in just a bit when we start talking about span towards the end. But the idea is that I'm hoping that there are some scalar weights x1 and x2 where v1 times x1 plus v2 times x2 is equal to this vector y. And then essentially that means we're talking about solving an augmented matrix. I can take v1 and v2 as column vectors, building a coefficient matrix, and I can augment with y and see if I can solve. Well, okay, so let's do it. So this first vector v1 becomes my first column. Second vector v2 becomes my next column. And I want to augment this with vector y, which had entries h, -3, -5. Now I can go ahead and I can try to do some row reduction. You know, really no wrong way to get started. Here I'm going to avoid working with h quite yet, but I can start working with it whenever I want to. Let me try, so it looks like row 2 is really nice. Let me actually use row 2 to get rid of that 7. I can use that 1 there to get rid of that 7. And I can replace row 3 then with row 3 minus 7 row 2. So I'm just going to rewrite rows 1 and 2 to start. Row 3, I'm going to get -2 minus 7 times 0 keeps my -2. 7 minus 7 times 1 gives me 0. -5 minus 7 times -3, so that's -5 plus 21 is going to give me 16. And then I can actually scale that third row. So I could do a -1/2 row 3. Let me rewrite the other rows. It's definitely a labor of love, right? Gotta do it. Let's divide everything by a -2, so I get 1, 0, augmented with -8. Now I can keep going through the reduction now, but now I'm going to have to start working with whatever's happening with h. So one of the first things I could do is I could replace row 1 with row 1 minus row 3. So I get 1 minus 1 gives me 0. -2 minus 0 gives me -2. And then augmented with h minus -8, which is really h plus 8. I can rewrite rows 2 and 3. And now what I can do is I can scale row 1. I could do a -1/2 row 1. So I get 0, 1, augmented with, and this entry is, I don't really know what it's going to be, but it's going to be h plus 8 all divided by -2. And I can rewrite rows 2 and 3. Now I think it would be a good idea to actually do a bit of a row interchange. And I would swap rows 3 and row 1. So I'm going to put row 3 at the top and row 1 at the bottom. So then here, my top row is going to be 1, 0, augmented with -8. Second row stays the same as 0, 1, augmented with -3. But then my bottom row is going to be 0, 1, and then I'm going to have here h plus 8 all divided by -2. And we can still make the comment that we want to make, but if I really want to be on my best behavior, finishing my row reduction, I now would want to go to row 3, my new row 3, and replace that with row 3 minus row 2. So let me rewrite rows 1 and 2. Row 3, 0 minus 0 gives me 0, 1 minus 1 gives me 0, and then I get h plus 8 over -2, and then minus -3. So that's going to give me h plus 8, all divided by -2, and then minus -3 is actually going to be plus 3. I think this maybe makes it a little bit more complicated, I think, to solve, but this is really the appropriate way to go about it. If I look at this, I can make a judgment and say, the only way this is going to be consistent if my coefficient entries in this third row, in the coefficient matrix, are all zeros, this augmented piece has to be 0 as well. So we'd say, well, okay, h plus 8 divided by -2 plus 3 has to be 0. And then I'd want to go ahead and solve for h. So I'd say, okay, now I'm just solving. H plus 8 all over -2 equals -3. And then I can multiply both sides by -2. So h plus 8 is equal to 6. I can subtract 8. So then h is equal to 6 minus 8 is negative 2. So this is what I get. Though realistically, I think it might be the easiest to solve it back here at this stage. If I notice what's going on, I'd say, well, the only way this is going to work and not give me something that's inconsistent is if negative 3 is equal to this h plus 8 all over minus 2. And that's what we wound up with when we started the process to solve anyways. Let's talk a bit about span. Span, I got to tell you about span. This is actually very important. We talk about span a lot in the course. So pay attention to linear combinations. Definitely pay attention to span. This is not going to be a one-time only conversation. So get the ears, to turn on the ears, whatever you got to do. If the vectors v sub 1, v sub 2, so on and so forth to v sub p are vectors in vector space Rn, then the set of all linear combinations, of v1, v2, so on and so forth to v sub p is denoted by the span of v1, v2, so on and so forth to v sub p, and is called the subset of Rn spanned or generated by those vectors v1, v2, so on and so forth to v sub p. That is to say, the span of the vectors v sub 1, v sub 2, so on and so forth to v sub p is the collection of all vectors that can be written in the form c sub 1 times vector v sub 1 plus c sub 2 times vector v sub 2 plus so on and so forth plus c sub p times vector v sub p, where c sub 1, c sub 2, so on and so forth to c sub p are scalars. And really we're talking about the set of all linear combinations. That's important. Let's talk about a geometric description of the span of vectors. So first, let's say let vector v be a non-zero vector in vector space R3. Then we'd say the span of v is the set of all scalar multiples of that vector v, which is the set of points on the line in R3 through that vector v and the 0 vector. And let's get sort of a visualization of this. I'm talking about 3 space, so I'll get my sort of graph in 3 space. And I have a vector v, and I'm saying it's not the 0 vector, so there is something to it. This would be my vector v. So vector v. And how would the span of vector v look? Well, let's do that in blue. So then the span of vector v would be all scalar multiples of this vector. So I could multiply this vector by 0 and get the 0 vector. I could multiply it by 1 and get the vector itself. But I could multiply it by 2 and double its length. I could multiply it by 3, 4. I could multiply it by, 2/3 and get a stunted version of it. I can even multiply it by negative values, move in this other direction. So what I get is, and it goes on in either direction, so I have to stop drawing it at some point, but I get this line in 3 dimensions in R3 through the vector v and through the 0 vector. You think of it like the origin, right? What if I have 2 vectors, though, and they're not the same? So say if u and v are non-zero vectors in vector space R3, v is not a multiple of u, or vice versa, then the span of the vectors u and v is going to be a plane in R3, a plane in 3 dimensions, that contains vectors u, v, and the 0 vector. In particular, the span of these 2 vectors contains the line in R3 through the vector u and 0 vector, and the line through vector v and the 0 vector. Let's get a picture. I'm working in 3 space. So this is my 3-dimensional grid, and then we have vector u. Maybe it looks like this. And then we have vector v. Looks like this. And what we're saying is that since I have the span of these vectors, I could first just talk about the span of u. I could say, well, my linear combinations, I can let all of the coefficients on v be 0 and just play with coefficients on vector u. And this is going to give me the line through the 0 vector and through vector u. And it would go in the other direction as well. I'm just not going to draw all of this. I want the picture to have some sort of meaning in its visualization, but it would continue on indefinitely in this region. Same with vector v, right? I could think about just scaling vector v by itself and get this sort of extension in v's direction. But then from there, I can really think about linear combinations and adding vector u and v together. And when I do that, I'd be sort of using the tail to tip method, where I'd be taking vector v, for example, and then adding vector u onto it, but I get sort of any extension of that. I can keep doing that along the way. But I could also do the same with vector u, as I could sort of translate along at this vector v and add vector v to it. I did sort of a poor job drawing it there, but I think you see what I'm going for. And I could keep sort of adding vector v. These should look parallel. And so on and so forth. And not even really stopping there, right? So I can continue on with this, and essentially what I'm doing, trying to make these look parallel. You could do a better job than me. But you end up getting this plane that is dictated by vectors u and v, that's where it gets its shape from, and gives me a plane in 3 space. Yeah, these are supposed to look way more parallel than they do, but I think it illustrates the point, right? So we get this plane dictated by vectors u and v, and it would move on indefinitely in the negative direction as well too. So keep that in mind. Well, let's go ahead and see if we can explore this notion of span a bit further. I want to list 5 vectors that are in the span of v1 and v2. Remember, span of v1 and v2 means the set of all linear combinations of v1 and v2. I just want to find 5 of those. So that for each vector, I want to show the weights on v1 and v2 used to generate the vectors, and I want to also show what the vectors are. Now right away, so I have vectors v1 with entries 1, 1, minus 2, vector v2 with entries negative 2, 3, 0. Right away, I can actually build something that isn't so difficult. You could actually go crazy with this. You could find infinitely many of these vectors, so certainly you can find 5 of them. So you might pick some different ones than I'm gonna, but let me show you what I think are the nicest ones, the easiest ones to find. So a set of all linear combinations of v1 and v2, so really sky's the limit. I can pick my coefficients. So one that I would pick, very nice, would be 0 times vector v1 plus 0 times vector v2, which would be 0 times the vector 1, 1, minus 2, plus 0 times the vector negative 2, 3, 0. And multiplying by 0 is just going to give me the 0 vector, killing off the entries. So I just get the vector with entries 0, 0, 0. The 0 vector is one of the vectors that lives in the span. So okay, not so bad. But then I can do something else with this. Here I can say, this is equal to the 0 vector. So I get the 0 vector as one of the possibilities. What else could I do? I could do 1 times vector v1 plus 0 times vector v2. And so this would be 1 times this vector 1, 1, minus 2, 0 times this vector negative 2, 3, 0, which we can probably see what's going to happen with this one. I'm going to get the vector 1, 1, minus 2 plus the 0 vector. And that's just going to give me vector v1 back out. In a similar way, I can use the span to produce vector v2. I could say 0 times vector v1 plus 1 times vector v2 is going to be 0 times the vector 1, 1, minus 2 plus 1 times the vector negative 2, 3, 0. And that's going to give me the 0 vector plus I get my vector v2, negative 2, 3, 0. I can add these entries together, so this gives me the vector with entries negative 2, 3, 0, gives me vector v2. So these are the easy ones, I think, to pick out first. We get, in the span of v1 and v2, we get the 0 vector. We also can generate vector v1 by itself, and then generate vector v2 by itself. But I need 5, so I need 2 more. Another great one to find would just be the sum of the 2 vectors. I could say, well, what about v1 plus v2? Or that's 1v1 plus 1v2. I can do that. So I'm going to get 1 times vector 1, 1, minus 2 plus 1 times vector negative 2, 3, 0 and that's just going to be adding these vectors together. So I'll sort of spare you the step in between. Multiplying by 1 isn't going to change the vectors. I add them correspondingly. I add the corresponding entries. I get 1 plus minus 2 gives me negative 1. 1 plus 3 gives me 4. Negative 2 plus 0 gives me negative 2. So this gives me vector v1 plus v2 is also in the span. And then you can do anything for the linear combination. So you could do, 3 times vector v1 plus 9,000 times vector v2. You could do v1 minus v2. All sorts of cool stuff. Let me do something a bit more exciting, though, for this fifth one, just to show how you can really get creative. Let's do 100 times vector v1 minus vector v2. So then 100 times this vector 1, 1 minus 2, and then minus this vector negative 2, 3, 0. And we'll say, well, how is this going to look? Well, I'm glad you asked. I would have 100, 100, minus 200, and then I can think about subtracting here. If I want, I can think like adding and bring that minus 1 as a coefficient in. So it'd be plus, here I get positive 2, negative 3, 0. And then I can go ahead and add these corresponding entries. So I'm going to get 102. 100 minus 3 is going to give me 97, and then negative 200. This is another vector in the span as well. But there's all sorts of these, right? For example, one I didn't do that I think would be easier to do is just the difference of the vectors, v1 minus v2. Or you can think of other combinations as well. So we have a lot of potential for many more of these. Hey, we'll talk more about span later. It's going to be a big part of our course. Thank you so much for joining me for this lecture video. I appreciate if you made it all the way to the end, so great to have you here. And no matter where you are and what you're doing, remember to always keep learning, keep dreaming, to always follow your heart. And I'll see you next time. But until then, I want you to take care.